Good morning. Today, I'd like to get a little bit more serious about things. I'd like to speak of space-time diagrams. If I have a physical object moving in the xy plane, and I tell you that the points that it passes through are these points, on the one hand, I have told you something, but on the other hand, I haven't told you everything. It could be that the motion along the straight line y equal x is uniform motion in a straight line. T here is time. Dx dt and dy dt are both constants, so you're moving at a constant speed. However, you could also be moving this way. X could be the cube of the time value, y could be also the cube of t. You are still moving along the same straight line, but the derivative of x and the derivative of y are no longer always constant. This is accelerated motion. Just looking at the xy's, I have no way of determining what's going on here. The way that we'll get around this problem is we'll add time to the picture, literally as a coordinate. I actually would like to draw x, y, z, and t in, but of course I'm unable to do so. I want to look at a couple of variations on a theme. Imagine that I had a point of the xy plane which was stationary. It might be one of my individuals in an inertial reference frame, for instance. The x and the y never change for that person, but the time coordinate does. In this so-called space-time diagram, if I look at the points x, y, and t, if I have a straight line parallel to the time axis, then this corresponds to the object being at rest. If the world line is a straight line, but it isn't parallel to the t-axis, that corresponds to uniform motion. In the case of x equals t cubed and y equal t cubed, t is, for instance, the cube root of x. If I draw the projection of the path onto the tx plane, I clearly see that it's not a straight line, it's curved. We would get a similar picture for t equals cube root of y. If you look in the space-time diagram at the path of an object through the diagram, if it's straight, we have either rest or uniform motion with respect to this inertial frame. If I don't see that, this is a clear visual indication that the object is accelerating. So far, nothing that we've said would have caused Isaac Newton the least bit of philosophical confusion or trouble. In fact, Newton would have thought that this was a very clever idea. Ordinarily, you can't tell just by looking at the picture whether something accelerates or not, but in these space-time diagrams, you can. The point of departure is right now. This is an experimentally observed fact. The speed of light in a vacuum with respect to an inertial frame is a constant. By adjusting our units of distance and time, we can make the constant take on any value we want, but that's just like changing from feet to yards or something. That doesn't change any physics. We're going to adopt units where c equals 1. We might, for instance, be using light years for distance and years for time, the speed of light is 1 light year per year. That's not the way people usually do their units. We'll talk about that another time. I want to imagine that I've set up an inertial reference frame. So I have space coordinates, I have my clocks, I have a time coordinate. I am deliberately not calling them x or x bar or t bar because that can easily lead to confusion. Because the speed of light is 1, if someone at some point of space-time were to send a light signal out along their positive space direction, then derivative of space with respect to time would be 1. The slope of the path in the space-time diagram would be 1. Or -1 if the light pulse was sent off in their left direction. In either case, any way you cut it, in a space-time diagram, a light ray makes an angle of 45 degrees with respect to the time axis. I'm going to imagine our old friend Fred. He is sitting at space coordinate equal to 0 within his inertial reference frame. There are two mirrors that are at rest with respect to Fred, and therefore with respect to Fred's entire inertial reference frame. At some moment in time, Fred sends a pulse of light off to the right, off to the left, where mirrors are located 1 unit of space away from Fred. After a while, the light rays hit the mirrors, are reflected, and eventually come back to Fred. I want to draw a picture of this in the space-time diagram of the inertial frame that Fred is at rest with respect to. We are free to label the beginning and ending time values and space values as we like. Fred is located at the origin, so he's on the time axis. Light rays emitted by Fred to the right or left must have slopes 1 or -1, depending on the direction. I'll call the time value at which Fred emits his light rays -1. Since the speed of light is 1, it takes 1 unit of time, as measured by the time axis, for the two light rays to reach their respective mirrors. After they hit the mirrors, they travel backwards from the previous direction and come together at Fred's location at t = +1. Now imagine that there is another inertial reference frame sitting around. The person at the origin of that reference frame could do this exact same experiment and get exactly the same results. So here's a philosophical question for you. Is Fred at rest with respect to the barred coordinates or the unbarred ones? The question makes no sense. I bring this up again because I don't want you to start thinking that one inertial reference frame is more fundamental than the other. I'm going to imagine that I have a second reference frame, and one reference frame moves to the right relative to the other one with speed v. That relative to the other one is very important. I'm going to put Fred's experiment at rest with respect to one of these two coordinate systems. So I'll finally go on and say it. Fred is at rest with respect to the barred coordinate system. The other inertial frame I'll just refer to as the unbarred system. Fred O bar is my small joke about the name of the reference frame. Joking aside, what does this experiment appear to be as measured by the network of the unbarred observers? Fred's world line, the path of points that Fred occupies in the space-time diagram, is the time axis of the barred system. So I'll go on and call Fred's time axis the t-bar axis, and likewise x-bar axis. The wedge that we're going to have to get into this new way of thinking is to ask ourselves this. The barred reference frame moves at speed v to the right relative to the unbarred one. Fred is at the origin, at the beginning of this situation. What does Fred's path look like with respect to the unbarred coordinates? Fred's path in terms of the unbarred coordinates is x equals vt. The x-coordinate is the speed times how much time has passed as measured in the unbarred coordinates. Or if you prefer, t is 1 over v times x, also known as the t-bar axis. So what I'm going to do is I'm going to draw in the unbarred coordinate system. I'm going to draw in Fred's world line, which is the t-bar axis, and see what we can figure out. I'm going to make up letters for some points in space-time. I'm going to call the point of space-time where the light was emitted A. I'll call the points at which it was reflected from the mirrors B and C, and I'll call the points where it comes back together D. I've got to pause and emphasize something here. The space-time is what it is. We can put down many coordinate systems, many inertial reference frames to look at it. The choice of the inertial reference frame is purely a matter of choice, a matter of preference. None of them are more important than the other ones. So let's begin. In this diagram, A and D are symmetrically placed upon the t-bar axis. When I go over to the other coordinate system, the transformation has to be linear because Newton's first law won't be preserved otherwise. A linear transformation will preserve this equal spacing. Not to say necessarily that the 2 points are the same distance in the new diagram than they were in the old one, just that they are symmetrically placed. This tells me the location, more or less, of A and D written in terms of x and t, the unbarred coordinates. Here's the key point. 2 light rays were emitted from A, one to the left, one to the right, according to Fred. They went off in different directions in the space-time diagram. They hit mirrors and eventually came back together at point D. Even though I'm using a different inertial reference frame, in the space-time diagram of the unbarred system, the light rays still have to make a 45-degree angle with respect to the time axis, which is now not the t-bar axis, but the t-axis. I had a minor drawing error, so ignore this part. Starting at A light ray goes towards the right at a 45-degree angle with respect to the time axis from point A. Another goes off to the left. Now, on the other hand, the light rays have to be received at D also, so I'm going to draw in another couple of straight lines representing that situation. Given my horrific drawing ability, this isn't as bad as it could be. In terms of the barred coordinates, the light ray started at A, ended up at D, and it changed its direction at point C. So we've more or less identified all of these line segments that make up the edges of our shape here. In particular, we can also draw in B and C, and of course, this is the x-bar axis in the barred coordinate system. And since I know B and C now, I can actually draw in the location of the bar x coordinate, the x-bar axis, on the space-time diagram of the unbarred coordinates. I said previously Isaac Newton wouldn't have had any kind of trouble with any of this on a philosophical level. If Newton knew about this constant speed of light thing, he probably would have drawn exactly this kind of picture, and then he would have spent the rest of his afternoon muttering, no, 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 and then eventually think, well, okay. In case it's not obvious what's gone wrong here, we'll talk about that in a little while. For right now, though, the t-bar axis, as measured by the unbarred individuals, is x equals vt, which you can write a variety of different ways. I would like to figure out the location of point C. That'll be enough to tell me the x-bar axis, because I know the origin is in common. Point D has some time coordinate, some t coordinate, not t-bar. I'll call that t coordinate alpha. The x coordinate that goes with it must be v times alpha. Because of the whole symmetric about the origin business, the coordinates of point A in the unbarred system must be negative alpha, comma, negative v alpha. This line passes through point D and has slope -1. Doing college algebra, it's easy enough to figure out what the equation of that straight line is. On the other hand, this straight line passes through t equals negative alpha, x equal negative v alpha, and has slope equal to 1. So it's also easy to figure out an equation for that line. Point C is going to be the point of intersection of those two lines. Setting the t-coordinates on the two lines equal to each other, it's a simple matter to find out that x must equal alpha. That's actually very interesting because that was the time coordinate of point D. Let's figure out what the time coordinate of this point is. I have two straight lines that this point is supposed to be on. As a sanity check, I'll make sure I get the same answer both ways. Putting x equal alpha into either one of those two equations results in the time value being v times alpha. So I do actually have my point of intersection. This line, which is going to be the x-bar axis as observed by the unbarred observers, is a straight line that passes through the origin and passes through the point where the vertical coordinate is v alpha and the horizontal coordinate is alpha. Since I now know the slope and I know the origin is on the straight line of interest, I can just write down that the x-bar axis, as measured by the unbarred coordinate system, is just the straight line t equal v times x. So to summarize, according to Fred and his friends, the space-time diagram for the experiment looks like this. According to the unbarred people, the experiment looks like this. It's hard to know how to express just how bad this is, though. Over here, the points on the x-bar axis are the points where t-bar is equal to 0. The points on the x-bar axis represent things that happen at the same time. As measured by the network of unbarred individuals, the reflection of the two light rays from the two mirrors, which happened at the same time, according to Fred and company, do not happen at the same time. We have to give up the idea of simultaneity. If I say two things happen at the same time, and I don't say anything else, then I haven't said anything. I have to say happen at the same time as measured by the O-bar network, or happened at the same time according to the O network. This means that some of our most cherished ideas have just gone out the window. One thought that I've kept mentioning over and over again as we've gone along is space is absolute and time is absolute. We've just found out that time is not absolute. It's going to turn out neither is space. This means we're going to have to become very careful about the words and thoughts we use to express things, because it would be really easy to have a long, deep-sounding conversation about something that doesn't even make any sense. Coming up next, I'm going to drop back to the orthogonal transformation stuff and briefly talk about what one might call the invariant circle. That's not what I'm really interested in, though. We'll immediately move back to the space-time diagrams and talk about the invariant hyperbola. Until then, I hope everybody has a good day, and I'll talk to you again soon.